Hello, my AB kids. This is section 5.8. We're starting the second half of Unit 5. And this is a super duper important section. There's a lot of questions on the AP exam that relate to this type of thing. So what we're going to be doing is looking at graphs of functions and thinking about what the graph of the derivative would look like, and vice versa. If they give you the graph of a derivative, what does the original function look like? And so there are key places on your graph that you're going to be looking for. I've got a few different colors and highlighters and things going on for this lesson, so if you want to grab those too, if you're a color pencil person. So first thing is you're going to focus on the slope of the function. Notice this is just f, because the slope of the function is the y value of the derivative. So we're going to put all these things into place. So I'm looking at, now you have to notice too, and this is really important, notice what they're giving you. So they're giving you, in this first picture, this is the graph of the original function. And they say, okay, if you're given the graph of the original function, sketch the derivative. So there's some key components that you're looking for. And if you think about it, if I look at my original function and I start on the left, reading it from left to right, this is all part of the graph where the graph is increasing, right? And then it goes decreasing. And then it goes increasing again. What do you notice about the slope at this location? And we've talked about this before. You should say, oh, the slope is 0. And over here, the slope is 0. Well, if I'm thinking of first derivatives, where a graph is increasing, I have positive slopes. And where it's decreasing, I have negative slopes. And then where it's increasing again, I have positive slopes. All right, let's put it together into the new graph. Graphing the slopes, because I'm looking at the original function and trying to do the first derivative. So I'm looking at the slopes of the original function. They're going to create that derivative graph. And so here I go. If I have a slope of 0, here's my point. It's got to be on the x-axis, right? That's a slope of 0. So both of my slopes of zeros get points on the x-axis. And if I think about what the positive would be, think of where the first derivative would be. In this section over here where I've got positive slopes, where it's increasing, I know my first derivative has to be positive. In other words, it has to be above the x-axis. And where I have negative first derivatives, negative slopes, it has to be below the x-axis. And then where it's positive, it has to again be above the x-axis. So what I've just drawn there in the highlight, let me put in a little underlay here, is this graph right here, positive, negative, positive, and that's what my derivative would look like. Now this should kind of make sense, because we've talked about how when you take the derivative, you're taking it down a power. And so if I think about what my original function was, it's some type of cubic function. And therefore, when I take the derivative, it should be a parabolic, quadratic looking thing. So it all kind of links together. But based off of the original function, if I'm trying to draw the derivative, I want to know what the slopes are doing. And so this is all about the slopes. So let me make a little note in my margin here. When I'm going from the original function to the derivative, f prime of x, that's this guy. I have positive slopes, or where it's increasing, same thing, are above the x-axis, and negative slopes where the function is decreasing are below the x-axis. Below x-axis. Now let me ask this question. Did it matter how low I made that go? Could I have made it maybe down here? And the answer is sure. You could have made it anywhere you want to make it, because as long as it's below the x-axis and doing that turnaround, then you know that you've got the right thing. So where it actually minimums over here is not what the big concept is. It's just that it has a minimum somewhere in that vicinity. So you could have made it lower, and that would have been okay. All right, now we're going the other way. This time they're giving you the graph of the derivative, and they want what the original function is. So now you're looking at an entirely different thing. Notice it's the same graph as what you had over here, but now it's the derivative graph, and you're going backwards to figure out what the original function was. Now, let me give you the gist graphically. This is a cubic function. What should the original function be? And so hopefully you're thinking, well, Jesus, should be a fourth power something, a quartic function. And you're right, because now you're adding a power on, you're going backwards. So just to give you a visual, you think that you should have some type of a quartic function when you're all said and done with this. So let's see how it works out. This time, if I were to make, this is the first derivative graph, I'm going to think of this in terms that you already know. You know how to make a sign chart out of a first derivative. What good is a sign chart of the first derivative? And the goodness of that is to figure out where you have maximums and minimums. So, okay, let's make a sign chart out of the first derivative. So it has, it's below the x-axis, so it's negative first. Then it's above the x-axis, so it's positive next. Then it's below the x-axis, and that makes it negative. And then it's above the x-axis, makes it positive. So if I were to make a sign chart just off this graph, not knowing where these locations really are, that's fine. I can tell that it goes negative, positive, negative, positive. Well, the goodness of that is if I'm decreasing and then increasing, that means that I have created a minimum. So I know I have a minimum here at this first location. And then I have a maximum at the next location, positive to negative. And then I have a minimum again going from negative to positive. So where are they? Well, this one here, he's my minimum. It went negative to positive. This one here, he's my maximum. It went positive to negative, positive to negative. Then I come over here, this is another minimum because it went from negative to positive. So those are locations that I can tell what's going on. All right. The next thing I can figure out from this about my original graph is where I have points of inflection. Now, if I'm looking at this particular graph, let me change my color. And now I'm thinking slopes of the first derivative. The slopes of the first derivative are the second derivative. Let me write that over here. Slopes of f prime of x are your second derivatives. Move that over so you can see it. All right, so let's think about that. If I have, what's my slope here at this location? At that top of the hill, my slope is 0, which means my second derivative is 0. If I look down here, same situation. My slope is 0, meaning that my second derivative is 0. Now, second derivatives, what are they good for? Second derivatives are good for where you've got concave up and concave down situations. So, if I look at this, all of this, I have points of inflection that are going to happen at these m equals 0. Because, see how it changes? If my slope is increasing and then my slope is decreasing, positive slopes, negative slopes, that means that this is a point of inflection, because it's changed from a positive slope to a negative slope. Down here, same idea, it changes from a negative slope to a positive slope, so I know I have a point of inflection here. Now from all of that, I can sketch this graph. The only thing that could come into play is a vertical translation. Maybe it might be that where I put my minimum, where I put my values for this may be lower or higher than what I actually am saying. So that can change. But the fact that there's a minimum there can't change. So the first thing I'm going to do when I graph my graph is put a minimum of some sort in this location. So let me just do that. Here's my minimum. Right, my minimum, I probably could move that over a little bit, but there you go, minimum there. This here, this place is a maximum place. And then I have a minimum location over in this area here. I'm going to make my minimum a little bit higher this time. I can put it wherever I want. It just has to be a maximum or a minimum in that location. All right, so let me connect them together. So if I connect them together with my maximums and minimums, here it is, right? Could I have made that smoother? Absolutely, I could have. But you get the same idea. So if I look at these places, my minimums and my maximums, they can't change. My points of inflection, did that work? Is this an area where it goes from concave up to concave down? Sure does. And then over here at my other point of inflection, is this about a location where it changes from concave down to concave up? And it does. So everything should kind of line up with these things. But I think the easiest way to do these is to locate your maximums and minimums, put them on, and then connect them. And make sure then it fits with what your second derivative is saying. So, and again, remember I started this problem and said, well, it's a cubic function. You should end up with a quartic function. And sure enough, you did. It is like a W, a quartic function. And so there it is. That's your curve sketching. We're going to do a couple examples. This is really super important stuff that you will definitely see again on the AP exam. So we're going to look at number 1 first. And question is, for number 1, what are you trying to find? What did they give you and what are you trying to find? So if I'm looking at this one, the graph of the function f, the original function, is given. So that's, again, I'm going to highlight it because it's really important to know which one you're looking at because what you're looking for changes. So I'm looking for the first derivative off of this. Well, that's like your first example from up above right here. So if I look at this thing, I know that my slopes, if I read this from left to right, my slopes are increasing over here. I have or positive over here because the function is increasing. So I know I have a positive slope. I'll put it this way, positive, from negative infinity to 2. Can I tell exactly what that slope is? And the answer is yes, because this one's a straight line. I know I can actually calculate out what the real slope is. So if I look at this rise over run, it's a slope of 2. So not only is it positive, I know it's 2. This is the original function. What do I know is happening right here? I know that I have a maximum at x equals 2. However, do you notice it's a pointy place? That means that the derivative doesn't exist. So I'm going to put that over here. First derivative does not exist because it's a pointy place. Well, how's that going to affect the graph? You'll see in a minute. And then all of these places from 2 to positive infinity, they all have negative slopes because it's a decreasing function. So I know I have negative slopes going from 2 to infinity. So how's that going to go? Well, I have a constant slope from negative infinity to 2. Here's what a constant slope would look like. Constant slope. That is 2. Positive 2. Here's positive 2 right here. All right, positive slope at 2. Goes like this. However, when I get to 2, there's a max at 2 that's undefined. So how do I say that? And what all I need to do on my graph is say open circle. Doesn't exist, right? So I would have an open circle at that location. Now, if I look at this, even though it doesn't exist at this place, what's the slope at this location? It's still a slope of 0. So I'm going to have a 0, but it can't exist at 2, remember? So it's got to be an open circle at 2, and all of my slopes to the right of this are negative. So all of my slopes to the right, let me go back to my highlighter here, all of my slopes to the right are going to be below the x-axis at some level. And so that is number 1, putting all those pieces together. A little tricky because of the pointy place, doesn't exist, kind of all has to fit. All of my slopes are positive 2 to the left of 2, and all of my slopes are negative to the right of positive 2. And so putting all those pieces, I find it easiest to make notes and then try to draw the graph, but I mean, you can do it however you would like. Number 4 is next on my list. The graph of f prime is given. Now we got the derivative graph. All right, I'm going to highlight that. We're looking at the derivative graph. Draw the graph of the original function. So I've got to draw the original function. Well, if I'm going backwards to draw the original function, let's come up with, first of all, a sign chart off of my first derivative. So I'm going to take my picture here, and I am going to make myself a sign chart. So I am at 1, 2, 3, 4, and I'm going to 1, 2, 3, 4, right? 1, 2, 3, 4, to positive 4. And I know that at negative 3, I have a positive above the x-axis. It's below the x-axis between negative 3 and negative 1. Negative. It's positive again from negative 1 to 0. And then it goes negative from 0 to 4. All right, so I just divided it up. The fact that it doesn't exist at these places, remember that it's where the first critical points are where the first derivative equals 0 or where the first derivative is undefined. So these are undefined places, and that's why they're on your sign chart. So my sign chart goes, I have a maximum over here at negative 3. I have a minimum, negative positive, and then I have a maximum at 0. All right, so there's one thing that I can say about this. The next thing that I can say is I have, let's check concavity, right? If I check where it is concave up for this thing, I'm looking at what the slopes are doing. So if I'm looking from the first derivative, trying to talk about the second derivative, I'm looking at the slopes. So f prime, double prime of x is what I'm looking for. I'm looking for the slopes of this graph. And I can tell that I am concave up from over here, concave up from negative 2 to 0, negative 2 to 0, because my slopes are all increasing. I should start from the left. So concave down's the first thing. All of my slopes are decreasing. So from negative 4 to negative 2. And then I was concave up from negative 2 to 0. And then over here, from 0 to 4, I'm also concave up. All of my slopes are positive. So negative, it's from 0 to 4. All right, concave down, negative 4 to negative 2. That was the only part that's decreasing. Both of these are increasing, and so therefore you go. Which means I actually have a point of inflection. My point of inflection is where it changes from positive to negative or negative to positive. That would be this location right here. So it went negative, positive, positive, which means that this is a point of inflection at x equals -2. All right, can we do this? Well, I need a maximum. I'm trying to find a good color here. We need a maximum at -3. So go to -3, and again, the vertical, where you put this vertically does not matter. Just that you've got to have a maximum at -3. So I'm going to -3, 1, 2, 3, and I'm going to put my maximum up here. Max. And then I have a minimum at -1. So the next thing I have is a minimum at -1. Minimum at -1. And then I have a maximum at 4. Well, 4 is an endpoint, so that just tells me that I need to end over here at 4 with some kind of maximum point. That also doesn't exist because this guy didn't exist. So I need to have some kind of a maximum. I can't do the full hill because I can't go past 4. So I'm just going to end off with that. So let's see if we can then put the pieces together for the rest of this. It starts at -4. Okay, so that has to be an open circle. I have a point of inflection at -2. That makes sense. Look at how it's going to change. Sad face, happy face. Comes to 0, stops. Just like I did there. And then I have a maximum here. But if I look at this, it is concave. What am I doing from 0 to 4? I am concave up. So somehow I have to make some kind of a something that's going to make this be concave up. So I'm going to make this a circle here, because remember at 0 it can't exist, and I'm going to go like this. So I'm going to take away my original, just so I can make it so it wasn't a straight line. It's now concave up. Let's check it out. I have a maximum at -3. I have a minimum at -1. I have a maximum at 4. I am slopes concave up from, let's start over here, concave down from -4 to 2, -2, concave up from -2 to 0. Okay, got that. And I'm concave up again from 0 to 4. So here is my graph. Keeping the open circles that were the open circles on the original one. Can you say that? All right, there's 4. A couple more and then we'll be done. The next page is a great page. I love this page, one of my faves. Looking at this and I'm trying to decide which one is its derivative. Now, the way that I first look at these is knowing that if I'm looking at the original function, then I want to find the derivative. If I'm going from a parabola, then I know I'm going to a straight line. I know the straight line I'm looking for is decreasing negative slopes and then increasing positive slopes. So it's a straight line that is negative going to positive. Where is it? Let's see my choices. Straight line going negative to positive. Ooh, I's the one. So this one, see how it's negative to positive? This is decreasing and then increasing. And so therefore number 5 goes with I. And you're going to take all of those and figure out which function goes with which derivative. All right, so good practice with that one. That's that page. Then we're going to number 22 is next on our agenda. If I look at 22, they weren't very specific in the directions for this. So I'm going to be a little bit more careful in how I approach it. But place the values. I've seen this as a multiple choice question on the exam before. Place the values of f of x, f prime of x, and f double prime of x in increasing order for each point on the graph. For these problems, if a point appears to be a max or min or point of inflection, assume that it is. So what you're doing with this one is figuring out like what f of a compared to f prime of a compared to f double prime of a would be. And you could do it for b, you could do it for c. I guess that's probably what they want you to do is for all of them. I'm just going to look at a for you. So if I'm at a, and this is, again, look at what they're giving you. Are they giving you the derivative? Are they giving you the original? In this case, it's the original. So if I'm looking for f of a, that means just what is the coordinate? That's a coordinate thing. So I'm down here, f of a is about negative 3.5. If I look at the derivative at a, well, the derivative is the slope. What's the slope at a? And you can see the slope is 0. And then the third thing they're looking at is your concavity. If I'm at A, am I concave up or concave down? And you can see you're concave up. It doesn't matter what the number is, it's just some kind of positive number. And so do you have enough information to put them in increasing order? And yeah, this is the smallest, this is in the middle, this is the positive. Oh, cool, I can just put my less than in here. So in increasing order, this is what it would be. The smallest is negative 3.5, then I hit a 0 for my slope here, and then I hit a positive. And again, you don't care what the positive value is, it's just is it positive or negative, because you just know that it's going to be bigger than what 0 is. So you can do the same exact thing for part B and part C for that guy, for points B and C. To answer that one, put them in increasing order. That's 22. Here comes the last one I want to do, and that is number 24. I thought this could be kind of confusing for you, so I wanted to help you with this one. This is a chart, interestingly enough. They give you the original function, the first derivative, the second derivative, and there are coordinates. Now this is the graph of, they're kind of giving you all pieces here. So this is a coordinate, what it's doing at 0, what it's doing at 1, what it's doing at 2, what it's doing at 3, what it's doing at 4. The graph is only going between 0 and 4. So the original function is positive, in other words, above the x-axis, below the x-axis, below the x-axis, below the x-axis. Okay. This is telling you that your slopes, well, if it's a slope of 0, then you know it must be some type of maximum or minimum, right? Again, slope of 0 must be some type of maximum or minimum. Slope of 0 must be some kind of maximum or minimum in the midst of this. This one where it doesn't exist, that's also going to be an interesting place to check out. As I'm looking at this, the first derivative. So all of these are decreasing, decreasing, increasing, decreasing. Then I go to the second derivative. The second derivative is negative, it's concave down, concave up, concave up, concave up. So let's go on and answer the questions now that we've got a feel for what the chart's talking about. Find the x-coordinate of each point which f attains a maximum value or a minimum value. Comes off of the first derivative. Where is the first derivative? Equal to 0 or doesn't exist. Right, undefined. First derivative equals 0. X equals 0 is one. I'm going to put my x's down and then we can decide if they're maximums or minimum. X equals 0 is one of my places. Next one where it, first derivative, 2. X equals 2. Next one, x equals 3. Next one, x equals 4. Now we know at 3 it doesn't exist, but it's going to be some type of a maximum. So I'll put that kind of in parentheses in the midst of this. How do I know it's a maximum? Because it goes, my chart goes positive to negative, increasing to decreasing. And so I know that's got to be some kind of a max, but it's not going to exist. If I go to 0, 0 is over here, and then it goes, my first derivative is negative. So that means if it's at 0 and then I'm going decreasing, it's got to be some kind of a max. If I'm at 2, where's 2? 2's here. The chart goes for first derivative negative to positive. Negative to positive means it's a minimum. And then at 4, over here at this guy, it's going from negative to that place, means that this has to be a maximum. I'm sorry, wait a minute. Hold on, let me take that back. Take that back. 3, negative, going negative. It's going down, so it's going down before it hits this. I was reading it backwards. Negative to that place would be a minimum. Okay. Let's see if the next question we got going on. Find the x-coordinate of each point of inflection. Well, points of inflection come when the second derivative changes signs. Negative to positive. Okay, so x equals 1. Negative to positive, positive to positive, positive to positive. They don't change signs. So the only one that goes with a sign change is this guy here at 1. And then they say, okay, now go and graph it. All right, so I have a maximum at 0. And again, it does not matter where I start this thing vertically, but I'm going to start it just for fun here at 1. All right, so I have a maximum at 0, meaning that it's got to be a high point, so it's got to be some kind of maximum. Remember, it doesn't go beyond 0. It's only between 0 and 4. All right, then I have a minimum at 2. All right, so let me put a minimum wherever I want. A minimum at 2. And then I have a maximum at 3 that I need to talk about. It's going to be a does not exist. So let me just connect what I've got so far going on here, and then we'll take it from there. So I have my original function is positive. Starts out. Oh, here it is. I had a coordinate 0, 1. I have coordinates. I forgot about that. That's cool. Hold on a minute. 0, 1. There it is. I have a coordinate at 1, 0. I have a coordinate at 2, negative 2. This is going to be very helpful. I have a coordinate at 3, 0. And I have a coordinate at 4, negative 1. Well, as I said, at 0 it's a maximum. At 2 it's a minimum. At 3 it's a maximum. And at 4 it's a minimum. Now as I connect this together, let's check out our function. It's going positive till I get to 1. And then it goes negative below the x-axis, still negative until I get to 3. And then it goes negative again, meaning that it's got to go this way. I'm making this pointy. Why do you think I'm making that a pointy place, not a smooth, curvy place? And so that's because, remember, the derivative didn't exist. I know there's a maximum there, but my derivative does not exist. So maybe we'll make note of that. So it doesn't exist there, so it has to be a pointy place. Let's see if it fits for all the rest of these things. My first derivative is negative, negative. All right, so it is decreasing and still decreasing. Then it turns to increasing from 2 to 3, and then it's decreasing again, negative, for the rest of that. So that fits. Let's check the concavity of this guy. It is a negative concavity. All right, concave down, I get it. And then it is a positive concave up, positive, positive. And then it is still positive concave up if I were to look at this. And that fits all of my scenarios. So there you go. That's number 24, and that, my friends, is section 5.8. So I will see you in class. Send me an email if you've got questions.